Hello, I'm Lorie Karnath, the managing editor of Molecular Frontiers Journal, published by World Scientific. I'm here today with Professor Omar Yaghi, who is the James and Neely Treasure Chair Professor of Chemistry at the University of California, Berkeley. Welcome, Professor Yaghi. It's a great pleasure to have you here.
Thank you very much.
So Molecular Frontiers Journal has recently published a very exciting article of which you are an author. It describes a vision for what is termed the air economy. However, before we discuss what this involves, maybe you could tell us a little bit about your background and key areas of scientific research.
Well, first, I'm delighted to be here, and thanks for taking the time to do this interview. It's great to see you again, Lorie. So I'm by training, I'm an inorganic chemist. And when I had started my independent career, I wanted to stitch molecules together to make new materials. And when I say stitch molecules together, I'm implying that we want to take molecular building blocks, well-defined molecular building blocks, and link them through strong bonds to make extended structures, or let's say crystalline materials. And so in a way, we started combining organic and inorganic together. And therefore, if you want to ask me about my area of expertise, it's organic chemistry, inorganic chemistry. And so because the field that we've created called reticular chemistry has combined both of these areas. And now it has really, because of how fertile this area has been, we've extended it to computer science and engineering. So I would say that I'm a reticular chemist.
Well, we'll be speaking more about that in a little bit, but let's speak first about what is a fascinating as well as hopeful concept that is outlined in your article. And in this, you consider three major challenges that the planet is already facing, and by all indications will continue to remain so in the foreseeable future. And these are, of course, access to clean air, clean energy, and clean water. And as you know very well, there are close to 2 billion people on the planet already living in water-stressed areas. Your message in part is that science already has or will be able to establish a basis for tackling and achieving these goals. Could you tell us a little bit more about this, what this means?
Yes, I call them the three stresses facing our planet, as you mentioned, the clean air, clean energy, and clean water. And I would say that humanity has never faced a problem that we couldn't solve when we put resources and we have the will to solve them, especially technical problems. These are technical problems, and we have at our disposal the periodic table and reticular chemistry that allows us to take elements from the periodic table to make new materials. And not just make new materials, but also be able to modify these materials nearly at will. Pinpoint changes can be made with precision in these materials. And the variety that you can have allows you to have access to a whole areas of chemistries that were unexplored before, and whole new classes of materials, as we have done with creating metal organic frameworks, MOFs, and covalent organic frameworks, COFs. These are porous materials that have extremely open structures into which gases from air can be selectively removed, such as carbon dioxide from air to produce clean air. But also that carbon dioxide, after it's captured, we can convert it into a fuel. And as you mentioned, also trapping water from air to make it clean water, and therefore this vision of the air economy.
And so how would you say that this differs from other efforts to separate gases from the air?
First of all, in terms of carbon dioxide removal from air, there are a lot of materials, but none of them can be modified in the way I just described with MOFs. So that's one. And two, the materials that I'm talking about, because they're linked through strong bonds, which is really the new aspect, chemical aspect that we have brought to mainstream, they are durable. So they are durable, meaning that they can remain in the device that is doing the removal of gas for many, many years without having to be changed or maintained. So this durability allows you to use the material over and over again so that you don't create another environmental problem. And at the end of the journey of this material, one can disassemble it and reassemble it in water using scalable procedures and zero discharge processes. So there's absolutely no waste in the processing of the material. Needless to say, something I did not mention is that what makes these materials special that no other material has is that they have ultra high porosity, meaning, let's say in 1 gram of a MOF or a COF, you have the surface area of an entire football field. That means that if I take 1 gram of MOF crystals, which will not exceed the size of a quarter or a coin, I can spread that on the nano level to cover an entire football field. Well, that's the space onto which we could bind gases from air. Gases such as CO2, water, and also, of course, hydrogen. Many other gases that are now being, MOFs are being used for those applications.
It sounds amazing. So what you're describing is how air as a non-polluting, cyclable and sustainable resource for carbon and water can be harnessed, powered by sunlight, and fed into a conversion cycle and used to produce fuels and chemicals via synthesis. Does this encapsulate what you mean by the air economy?
That's an aspect of it. That's turning carbon dioxide into a fuel, trapping it first, then turning it into a fuel, either by using chemicals, non-biological chemicals, or by using microbial processes, so that you can take CO2, generate hydrogen electrochemically, combine the two into a microbe, produce an important feedstock like acetic acid or formic acid, and then feed that into another microbe to make a whole array of chemicals and fuels. So yes, that's one part of the equation that creates the clean fuel and the clean air. And of course, trapping water from air to make clean water is the other part. So yes, indeed, as you mentioned, air is a plentiful resource that we can tap into, not only cleaning it, but also generating useful things that we need to sustain our society.
So one of the things that you mentioned is that during the course of history, over and over, it's been changes and innovations in materials that have led to civilizations progressing and evolving, etc. Our world is transformed over and over, due to innovations such as the use of cement, glass, steel, petroleum, plastics, paper. There's so many things, many of these with penalties. Now, you mentioned just a little while ago, which was going to be one of my questions, is there some sort of unbalance or something that this process creates? Are there things that we should be wary of that could create more challenges ahead?
Well, I agree with you. I think progress creates great things, but also sometimes at a cost. And how do we move forward with less liabilities and more benefits? And I think it's all boils down to the atom and the molecule. And if you know how to manipulate those with great precision to create a whole new world of materials that covers the entire periodic table, then you have fortune on your side. And public awareness also is changing. We are much more aware of the issues facing our planet today than we were 100 years ago. So I think that's the innovation I'm talking about. And so whatever problem we might face in future as a result of new technologies, new progress that we are making, on our planet, being able to innovate is a certainty, provided we have the resources and the will to allow our researchers to go in that direction.
Well, for sure, obviously we have to do something. So I wasn't trying to be negative, but I'm just asking, since we've seen over and over in the name of progress, things that have led to the well-being for many, oftentimes have led to some of the environmental sustainability and health challenges that we currently face. One of the things that I could be perhaps from my perspective at least, the most important is that what you're offering in a way is something that could allow for autonomy in certain regions where they're geographically resource challenged, and others that are, logistically resource challenged, and perhaps provide for a more equitable distribution of our resources, because the resource allocation is going to be something that we all are going to have to very much focus on going forward.
I agree fully with the sentiment of your question. I mean, you look at some of the resources on our planet, it took millions of years to make them, and we have been using them, ravishing them in a course of just 67 years since the Industrial Revolution. That's unnatural. So we have to start thinking with awareness. I believe in progress and innovation. Those materials that you mentioned have served tremendous progress for civilization because they created global industry, have improved our standards of living. They have contributed to better health. They have contributed in a great way to our civilization. And I believe that the future is different. And those same materials, while they may continue to serve us very well as they did before, we have problems that require a new kind of materials. And what I am saying is that we are able to harness the power of the periodic table through reticular chemistry. And one aspect of, let's say, future industries that we envision is the air economy. That here is potentially an area of great industry, global industry that could develop that is much more sustainable than making cement. Okay, so I think that's the essence of what is mentioned there. Take, for example, Lorie, the cell phone. The cell phone is an important progress in facilitation of our communication and so on. You can't deny the importance of the cell phone. The cell phone has more chemical elements in it than our body. Okay, so that just tells you progress, at least in my world, requires us to understand the periodic table and how to deal with the elements of the periodic table to make new materials. And I would say that's what's going for us so far in present day chemistry.
Because when you think about it, what some of the alternative options that are being offered is that everybody go back to how life was 300 years ago, which is not going to be very feasible either. So what you're offering is perhaps a path forward that offers true progress. But what I especially like is that it can also help maybe equalize some of the inequities that we do see around the world, which will lead to a better use of resources and individuals' well-beings.
Lorie, you're absolutely correct in what you just said. Is, if you take harvesting water from air or carbon dioxide to turn it into a fuel, that puts you directly off the grid. So now, instead of the individual dependent on their locale or their state to provide them with water in a pipe in the grid, now you can have your own device and you can live anywhere, outside the city, in the city, and be in control of your water. You produce your own water using this device. boy, that is a tremendous difference from what we have today. In most of the world, in the arid regions, there is lack of water. In the watered regions of the world, most of the time we have questions about the purity of our water. And in many places in Southeast Asia, water is dirty, it's not clean. Mm-hmm. And so even in the watered regions of the world, there's water stress, a different kind of stress. So imagine being able to generate clean water independently of the grid and personalize it to your own need. Perhaps the vision of water independence becomes real. Mm-hmm. And therefore we could live our lives differently. Yeah.
I have to say, when I listen to you, it all sounds just amazing and almost like science fiction, except that I did see you 2 years ago produce water on a stage in Stockholm. So I know that you're very capable of doing this. So, but it is amazing to think about this vision, but it seems like at the same time, this is a direction in many ways we're going anyway, perhaps without the tools to accomplish what you're saying. But now that people are working more from home and a lot of collaborations are remote and things like that, the ability to be that autonomous fits very much into a lifestyle that's shifting anyway, in part due to the pandemic, but even before that.
More and more, we want things more personalized. We want to have more control over the things that we care about. And, the response of the world to the pandemic has not been admirable.
I agree.
Clearly, very large institutions and governments have, to a great extent, have failed us in protecting us from the pandemic. We could have taken earlier steps, faster. We could have adapted faster. We could have prepared better. But yeah, we are more and more. We're moving towards a more, let's say, technological society, and more individualistic needs are becoming important.
Yeah. So. But what you're offering in a way is a way for us to be able to live remotely and autonomously if needed, and even if not needed, provide perhaps more ability to just live in places that you might not have been able to before. So my question is, how do we achieve this vision? Where do we go from here?
Well, I think first and foremost, you have to have a technology that works. Mm-hmm. And the rest falls in place. The technology that I've described 2 years ago in Stockholm, I showed you that it works. And now, 2 years later, we have government agencies who are funding directly that type of research in my lab and in other labs. And we have a well-defined objective, which is to take basically those first prototypes and turn them into devices that are durable and that can be much more productive than I showed you, and much more energy efficient. And since we talked, several startup companies have taken up the challenge of commercializing water harvesting from air. So, how do we get there? Well, it's slow, but we are making progress. It was developing reticular chemistry did not happen overnight. It took 20 years to perfect the chemistry. But now everything that we've worked on for the last 20 years have come to be useful in addressing one of the most vexing problems on our planet, and that's water. And CO2, MOFs and COFs are at the forefront of solving the CO2 problem as well. So from my perspective as a scientist, we get there by allowing us to innovate, by allowing us to do the things we do best, which is research, unhindered, unconstrained research, so that we can make innovations that would impact on solving these challenges. So I would say that within the next 2 to 3 years, you will see water harvesting devices in the market. They're already in the market, but those devices work differently and they don't work in arid regions. Okay, but these devices I'm talking about, they will work anywhere in the world at any time of the year, whether it's very, very low humidity, like in the arid regions, or very high humidity.
And so what do you see as the biggest obstacles still towards reaching some of these goals? Is it on the research side? Is it on the business side? Is it on the making it affordable side? Government side?
I don't think that there's any stumbling blocks. I think that we are progressing, just like any new development. There's always a chorus of people that say it's not going to work, it's too expensive, and all the other things that ultimately we have over the years proved those doubters wrong. And well, that's the nature of working at the frontiers. So I don't think there are any stumbling blocks. I think we have a very, I think, important and fertile collaboration with GE on making the next generation devices. And what other company could be better than GE at managing air and energy and mass transport systems? So I think that it's very promising. Well, I know it's very promising, and the technology works, and the rest is simply a matter of time before we can see these in the market.
So if we speak for a moment just about reticular chemistry beyond what we're discussing now with the air economy vision, what do you see as some of the applications for this? Sounds like it can go in almost any direction, but I'd just like to hear from you what you're thinking.
Indeed. So once you know how to control matter on the atomic and molecular level, and once you can vary the components from across the periodic table, from the elements in the periodic table, the applications are nearly limitless. So there are, as of today, almost MOF and COF research, reticular chemistry research, is being done in over 100 countries around the world. And so you can imagine there are thousands of researchers that are engaged in this endeavor, and they're working on many different applications ranging from gas storage and separation of gases, storage of hydrogen, for example. We discussed CO2, we discussed water separation, but also ethylene, difficult separations. There are many applications dealing with imaging, bioimaging, cancer therapeutics. There are many different applications that are being pursued by others involving both biological applications and materials application. So I like to say that these are the materials of the 21st century. And already we are making progress in addressing some of the big problems that have been there for a long time. We definitely have done that in solving the intellectual problem of building structures from molecular building blocks to make durable materials. And this is why today I can sit in front of you and say I can harvest water from low humidity air, where no other material can in an energy efficient manner. So that is directly a result of chemistry and the work that we have done in reticular.
So beyond what we're discussing today in terms of alleviating many of the climatic stresses on the planet, how do you see this changing the world? Each one of those different breakthroughs that we talked about earlier did change the world in one way or another, but what do you think you will credit this most with, how it'll change how the world in general, but how all of us also think about our lives and our futures?
I think one of the fundamental things that this area has done is that now emerging scholars, young scientists, can imagine a structure that they want to build and go to the lab and actually build it, be successful in building it. when I was a student, I could imagine whatever, and I go to the lab and there is no way I could make it because we used to call it shake and bake chemistry. There was no design, there was no process by which you can take well-defined entities and hook them together, stitch them together. So like Lego blocks, okay? And make crystalline materials that you can actually characterize and study, and then if you need to, modify without them losing their structure. So this progress really has taken chemistry from the discrete molecules into the extended 2D and 3D. So I would say the very first thing that it has transformed is the way we think about making chemical structures, materials. Is that now a researcher can go into the lab, they can imagine a structure, go to the lab and make it. So could we in future just have a web interface where we ask this interface to spit out what kind of materials are out there that have these very properties that I want for whatever industry or whatever application I want? That's my dream. My dream is to be able to have a system in place that allows anyone, not just chemists, but anyone with a prepared mind to spell out what they really want and what properties they need in that material and get it in the mail, okay? or be able to make it in their kitchen. So on a basic science level, this is only the beginning, because if you look at how biology operates, it operates on sequences. DNA is great because it has unique sequences that code for specific properties for synthesizing proteins and so on. But outside biology, we don't have this concept of sequences. We've never been able to transfer this powerful concept of sequences into extended structures, because anytime you put multiple components together in a synthetic material, you get a mess. But what reticular structures have done, because they are robust, you can use that backbone onto which you can then superimpose that heterogeneity. And so you can put, what I'm trying to say is that you can covalently bind sequences of chemical functionalities onto the backbone of a MOF or a COF, such that if I'm a molecule floating inside the crystal, what I'm looking at are sequences of chemical information. And these sequences potentially can code for very specific properties, such as capture of carbon and converting it to a specific molecule or fuel that you can't make any other way. So that's where we're heading. We're heading into a world where making materials is routine, any kind of material is routine, and then tailoring it through these sequences for specific properties can be done with great ease. That's my dream.
Sounds like a good dream. So it sounds like this is a very multidisciplinary approach towards science, correct? I mean, you're involving many different realms, which is not always so typical, although we see that more and more perhaps these days. But what you're talking about really involves almost every aspect of science.
It does. I mentioned that we combined organic and inorganic chemistry, two fields that are taught separately, and many departments have separate faculty that sometimes fighting over resources and whatever, and classes and so on. But two separate fields into one. But also the fact that we're taking now these materials all the way to engineered devices has also involved a lot of machine learning, artificial intelligence, robotics, and engineering, mechanical engineering, especially electrical engineering, chemical engineering. So a typical graduate student in my lab is getting exposed to not just the old-fashioned chemical synthesis, but also being able to do so in this for solid state materials and studying and characterizing them using a multitude of techniques. And they are also exposed all the way to how this material would be placed inside a device, and then ultimately how the device performance can be controlled by controlling the molecular aspects of that material. Just to give you an example, in one of these MOFs that take up water from air, you can just replace in a linker one atom, a nitrogen with an oxygen. And to any chemist, that's a trivial change. We call them derivatives. But to the device performance, it's tremendous. It's a difference between 100 people getting water or 150 people getting water. So that's the effect of control in chemistry. And we are doing it in extended 2D and 3D structure.
Now, do you see, you alluded to this early on in our discussion, but do you see this, these materials having potential for delivery of medicines, for example, and actual biological functions and things like that?
Many of my colleagues, some in Europe and some in Asia, are pursuing programs on drug delivery with these. And in fact, there is already a drug that is going through trials as a cancer therapeutic. So yes, like I said before, I think that there are many, many different applications, and I've written papers that outline these, ranging all the way from things related to the air economy, to catalysis, to pharmaceuticals. For example, let me give you one example. Pharmaceuticals and metabolites are important, of course, but they're very difficult to crystallize because they're not very symmetric. So one can use the MOF because the MOF is crystalline. You take one crystal of a MOF and you expose it to these molecules, the drug molecules or metabolite, and the molecules go in, and because the MOF is designed to specially bind that molecule, and they sit inside the MOF. Now I can take that crystal and get a crystal structure, identified the drug molecule through X-ray crystallography. That's an application that helps in studying what these metabolites, the mechanism of metabolism in our body, the way drug molecules are being metabolized in our body. This helps a lot in identifying the absolute configuration of these molecules, which is essential to looking at drug action. So that's just one little application that has tremendous impact on the pharmaceutical industry.
So if you're a science student right now in high school or university, what do you recommend that they study if they want to go into reticular chemistry? It sounds a bit overwhelming with all the different fields combined. What would be your recommendation?
Well, my recommendation is to study atoms and molecules, and that's you can study them from a physics point of view and measure in physics, or you can study them from a chemistry point of view or from mathematics. There are many different ways at understanding atoms and molecules. Chemistry is just one way. So obviously you have to be in one of the basic sciences if you are interested in innovating in that space. I think if you're interested in the practical aspects of molecules, engineering is, of course, is a more appealing in that way. But we need to care about the things we don't see. We need to study those things, and there's a whole world that is behind many things that we see. So that's what really attracted me about chemistry, is that I wanted to look deeper and deeper into the things that we see every day, and understand, why do they have that color? Why do they behave the way they do? And it all boils down to a lot of chemistry. So yes, I think the interest in atoms and molecules is a very good way to start. Sometimes I give talks to general public, and young students ask me, how do you become passionate about something? How do you get interested in chemistry? And my answer is always, just be curious and study things in detail. Study anything in detail. And then you would become passionate about an aspect of our world. So the key is to look into things in detail, and then that would allow you to find opportunities to ask important questions and get you interested in the topic.
I think that that's very good advice, not just to become a scientist, but for anything anyone wants to do in life. So I greatly appreciate your time. And before we leave, is there anything else that you just would like to mention or speak about?
No, I think you asked a lot of very good questions, and I hope I've given you responses that you can use in this interview.
For sure.
Yeah, I'm delighted that you have time to do this, and I'm happy to participate in it.
Well, thank you, Professor Yaghi, and the pleasure was all mine. And I look forward to hearing much more from you, and we look forward to seeing some of these developments in action. So
Thank you,
so
Lorie. Yeah. Okay. Take care.
You too. Bye-bye.